Great. Right. So thank you for having me. I hope this will not fall off. Great. Thank you for having me. Today I'm going to be talking about causal effects in MPDAGs and mostly focus on the efficient estimation part here in the linear setting. Just trying to figure out how I don't get the. Right. This is joint work with Richard Guo, who is here, and he gets all the credit for like all the great results we have. Yes. Okay, sure. No worries. All right. So some of you may have seen some versions of this talk previously. I apologize for that. I've also given a talk in Simons for people who have been longer term earlier here. If you've seen that talk, that should be helpful for understanding maybe some pointers here. If you haven't, you should not worry about it. It should not be necessary. Okay, great. Right, so, and also some slides may seem familiar in that case. Okay, great. So the goal for us is we want to estimate some total causal effect of some XA on some XY. So XA for us will be treatment, some type of treatment, and XY will be the response. And ideally, right, you want to do this from randomized control study data where you intervene and set XA to a certain value and then monitor kind of the change that happens in the response as kind of the result of that setting, right? So I'll use this notation of do intervention. So do XA means that you have an intervention that sets these variables to some fixed value XA. And the issue for us will be that we will want to use observational data to compute this rather than randomized control studies data. And a major challenge there is that this interventional distribution of the response is different than this observational kind of quantity here. Okay, great. Okay, so how can we kind of do this? So I will use this graph kind of as a running example throughout. And I'm going to assume, right, this is a causal directed acyclic graph. So acyclic means there's no feedback loops. And additionally, each of the nodes in this graph represents a random variable. And each of the edges in my graph will be a direct causal effect. Right, so if I change A, it will affect B in some way and so on. Additionally, throughout, I will assume I'm interested in the causal effect of A on Y. And throughout, I'm going to assume that A just is like a single variable and Y is a single variable. That is not required for this results to go through, but it just makes things simpler to talk about. Okay. Right, so if you have observational data, you kind of have data that comes from this graph, and we want to use that data to kind of estimate our causal effect. And if we were to have the data from a randomized control trial, then the data would come from a graph that kind of looks like this, right? Where you've kind of intervened, you've set A to some fixed value. So now this E no longer can impact A, but whatever you've set A to can still kind of propagate downstream from A. All right. So we don't have data from this, we have data from this, but we want to kind of pretend as if we have, I guess, data from this and still be able to estimate the total causal effect. And this is like the notation slide, right? So, what I'm going to use here, so I'm going to assume we have this intervention that sets variables XA to some fixed value A. And then I'm going to talk about something like an observational distribution and an interventional distribution. And I will say that a DAG is causal if this observational distribution, but also the interventional distribution all factorize according to this DAG, right? So this observational distribution factorizes in this way. So it's each node given its parent nodes. And the interventional distribution factorizes in kind of exactly the same way, except that you drop the term that depends on A. So in this simple graph here, this is what that implies, right? So in this interventional distribution, we just kind of lose this term, but this term here matches this term here, and this first term matches the first term on this side. Now, in this project, I will additionally assume that my data is generated by a linear causal model, which in this case would be something like this. So in the observational case, I have this linear causal model. So, right, so XA is a function of XB plus some error. So it's some edge weight here on this edge plus some error, and Y is then equal to some constant, right, gamma BY times XB plus gamma AY times XA plus some error term. In the interventional setting, I will just choose to set my XA to a fixed value, and that will then propagate also downstream. So additionally, I'm assuming that these errors here are mutually independent, have mean zero and some constant and finite variance. Great. And by the way, I will refer to this as a structural causal model, or SCM. So SCM for me is structural causal model, not synthetic control model, like in the previous two talks. All right. Great. So how do I define a total causal effect? So total causal effect can be defined as some change in the response, right, due to this treatment. And so in this linear setting, it makes sense to define it in this way. So it's kind of this difference between these expectations of XY in one intervention and expectation of XY under a different intervention, where like these differences are just changed by one. In the linear case, this is also equivalent and kind of just taking this derivative of the expectation with respect to XA. I will say that a total causal effect is identifiable from observational data if you can express this distribution as a function of this observational distribution. Great. So now if you've seen the previous talk or the previous slide, you know that if I give you a causal DAG, then you can identify every total causal effect, right? So we have this interventional distribution of Y. It's just a marginal of the joint interventional distribution. And we already know how that factorizes in terms of the DAG, if we have the causal DAG. So you can identify this effect in this way, and then you can plug it into this computation to kind of compute your total causal effect, actually. This is something that I will call the G formula, generalized G formula, truncated factorization formula, manipulation density, whatever you like. I will call it the G formula. Additionally, sometimes you can identify these causal effects through a different formula. In particular, I will talk a little bit about adjustment. So with adjustment, so if you have a set Z that satisfies certain conditions, it will be an adjustment set, which means for us that this interventional distribution can be expressed in exactly this way. And so these two formulas will induce two different estimators of the causal effect, and I'll do some comparison of these two essentially. Right. So let's go back to our graph. So here I'm assuming now the data is generated by, in matrix form, this system, right? So I have X times this gamma matrix where this element gamma ij is non-zero, or is zero if you don't have that I is a parent of J. So the only allowed non-zeros are the ones where A is a parent of B and B is a parent of C and so on. Okay, so all of the same things we had before. Okay, great. And we are interested in the total effect of A on Y. So the total effect for us, it just means that it propagates through these edges on this causal path from A to Y. And so in this linear setting, we know even from Wright back in the early days that by kind of path tracing rules and using that gamma matrix we had on the previous slide, you can express this total causal effect as these sum products of these edge weights, right? So it will be kind of this gamma AB times gamma BC times gamma CY plus gamma IC times gamma CY, right? Great. And also by G formula, right, we can just plug in what the G formula is here, and that kind of actually also gives us the same computation. So this G formula kind of based estimator, if you look at it, it's just the expectation of XY given XC and XC. Same thing for this gamma CY. This suggests kind of a plug-in estimator where you estimate essentially all of the elements of your matrix gamma by regressing each node on its parents. From that, you get your estimates for the little gamma CY. So you get the little gamma CY hat, you get the little gamma BC hat, and so on. And you can plug that in and get your tau a y hat, right? So that's what the G formula kind of suggests you should do based on this formulation here. Right. Now, in this case, for this particular graph, we can also estimate this effect and identify and estimate this effect in a different way. So we here know that this E, it's a common cause of A and Y. It's the only common cause, so it's an adjustment set. So if you adjust for E, right, if you kind of block this path through E, you will also get the causal effect estimate. So since this is an adjustment set, you can also kind of look at this causal effect as computing it through this formula. And what this formula here would suggest to you in terms of an estimator is an estimator where you estimate this total effect as the least squares coefficient in just this regression of y on A and E. So that's where the adjustment name comes from. It's just an adjusted regression for E. Right. And so what we were, I guess, thinking about is which of these estimators is more efficient in this setting, and what happens if you don't know the causal DAG. All right. So which estimator is more efficient? This is kind of a question that's been thought about for a long time. It's not nothing new. So if you assume Gaussian errors and you assume you know the causal DAG, then there's work by Hayashi and Kuroki, for example, that says that this path tracing estimator, so the plugin where you kind of estimate each of the gammas and plug that in, that is more efficient than any of the covariate adjustment methods that you can use. Right? It's also not surprising because in this case, that just happens to be the plugin Emilija estimator. Right? So that's not super surprising. But what happens if you don't know the DAG? So I guess this is where our curiosity was piqued, and also, you don't have to assume Gaussian errors. So what if we do not know the DAG? So this is kind of the setting where I usually, I guess, work in. That this is not something, if you have a linear Gaussian data, that you can learn just from data. So from that data, you could use a structure like this. And I don't know if people can see that these are gray directed arrows still. And then all of the other edges here are undirected. So this is a graph known as completed partially directed acyclic graph, or a CP DAG. And as you can see, it has both undirected and directed edges. And the undirected edges mean here that we don't know whether this is like A causes C or C causes A in the underlying DAG. So you can think about this as a summary graph representing an equivalence class of graphs. And one of these is your true causal DAG. You just don't know which one it is. Right. So now additionally, I'm going to add some domain knowledge. So let's say I will add the domain knowledge that E causes A. And I will propagate this knowledge using the assumption that my underlying graph is a DAG, so acyclic, and certain other rules. So using these orientation rules of Meek, I'll propagate this knowledge to get some more orientations, right? So now I have something called a maximally oriented partially directed acyclic graph, or an MP DAG. That represents essentially something you can learn from observational data and perhaps some domain knowledge and so on. Right, so this still has some undirected edges. So it still represents an equivalence class of graphs. Now it's just a kind of a shrunken down version of the original equivalence class of graphs. Yes?
You're claiming that all these blue arrows are consequences of E to A edge?
Yes. Yes, and that's what I'm claiming. It's so here, the reason that they're all implied because if you had had the arrow pointing the other way, you would have another V structure, and that would imply some additional conditional independencies.
Oh, so where were you making assumptions about V structures? That wasn't clear to me.
Oh, I see. So a CV DAG kind of is uniquely identified if you know its skeleton and you know these V structures. So here, this is a V structure. What that means is just that you have both of these pointing into Y, but they themselves, E and C, are not adjacent.
Okay, so implicit in all these undirected edges is that there's no V structures.
Yes, there cannot be any V structures there. Right, great. So we are here. Awesome. And so we are wondering kind of what do you do here? How do you identify and estimate effects efficiently here? So in my big framework slide, we are in this part. This is where our interests are. So the idea is we have some observational data and perhaps some background knowledge that we have used in the past to learn this causal graph. I do assume that I have no latent variables, which is a very strong assumption and one that I would like to get rid of at some point. So this causal graph for us can be a DAG, CP-DAG, or an MP-DAG, but just note that this MP-DAG kind of is a bigger class of graphs that subsumes these other two. So you can think about a CP-DAG as kind of an MP-DAG where the background knowledge you added was like not informative at all, and a DAG where this background knowledge was fully informative of the causal structure. You can also kind of think about this picture slightly differently, which is that you started from a DAG, right? That you believe is kind of true, but perhaps you're not sure about some orientations. So you've removed them from your graph. And that's how, so you started from a DAG and removed some information, and that's how you ended up with an MP-DAG. So either way you think about it, it's fine. And right, we want to use this graph to, well, identify and then estimate the total causal effect. So, so I will focus on this efficient estimation. So I will assume that my effect is already identified, and to do that, I will use a result, previous result. Okay, so here is the results. So we've so far talked about DAGs, and I've shown you kind of the adjustment stuff in DAGs and this G formula in DAGs as well. Now, there are criterion that allow you to kind of identify all valid adjustment sets in these CP-DAGs and MP-DAGs as well. And this previous result that I mentioned, that just generalized this G formula to these CP-DAGs and MP-DAGs. So now we can use these two kind of estimators in both of these cases, and knowing what we know from DAGs, we are, I guess, expecting this formula, this kind of way of estimating things to be more efficient than the adjustment one. So that's, I guess, our claim to fame. Another thing to know is that this adjustment here in also of these three graphs is kind of sufficient for identification. It's not necessary, particularly if you have, for example, sequential treatments where one treatment affects the other treatment. You often will not be able to estimate those that joint effect with adjustment, but you can still use the G form. Okay, great. So let's talk about kind of previous results. So there's several results actually on comparing estimation here. So Henkel et al., Witte et al., and Rudnitsky and Smukler, they all graphically characterize what would be kind of an optimal covariate adjustment set in all of these graphs, right? So if you just limit yourself to just estimators that are based on adjustment, what is the best estimator to use in terms of efficiency? So they all actually agree on just one type, one definition of which is the best adjustment. However, as pointed out by kind of these arrows, implication versus kind of equivalence, covariate adjustment is not complete for estimating all identifiable causal effects. So the question is, can we kind of leverage this kind of new result that generalizes the G formula to get kind of better efficiency in the case of CP-DAGs and MP-DAGs? Right. And so now we go back to our linear system, right? So this was our original DAG. And now I'm moving to this world of an MP-DAG where I don't know the orientation on these two edges. Now, what happens to our system here, right? Previously, what we wanted to do is just kind of estimate all the elements of this gamma and then do a plug-in estimator based on these parts. But now our gamma is not identifiable because we don't know kind of these orientations. We don't know which gammas should be zero, which ones should be non-zeros, essentially. Okay. So I'm going to rewrite this problem into something that will then give me a solution. So I'll say, okay, let's consider what are these buckets, which is just a short word to use instead of this thing, which is the maximal undirected connected components in this MP-DAG, right? So what are the buckets here? So I'll just remove all the oriented edges so that we know. And so now our buckets are these four. So E, A, those are single node buckets, and then B, C, D is a triple, and Y. And so they're ordered here in the topological order, in the causal ordering in the graph, right? So E comes before A and so on. Okay, great. So now I know that between these buckets, I have all of the edges oriented. And actually, in this previous paper, that implies to me that these effects between the buckets should be identifiable, the causal effects between. Within the buckets, the causal effects are unidentifiable because, I mean, obviously, I don't know whether B causes C or C causes B. And there's also another nice property here, which we exploit to get our result. which is what Richard's called a restrictive property, which is that each node in a bucket has the same set of out-of-bucket parents. What that means here is that if A is a parent of B, it also must be a parent of everything else in this kind of maximal undirected connected component. All right, so I'll use that to rewrite my linear structural causal model. Great. Okay, so I'll just take all of those x's that belong to one bucket, and I'm going to split the gamma coefficients into the coefficients that come from the out-of-bucket parents into the bucket, and all of the other coefficients. So this will contain like all of the coefficients within the bucket, right? So for example, if I look at my BCD bucket, this part will just be all of these gammas, and this part will hide all of these within bucket gammas. So that's the only thing happening here. And we still have our errors on the whole bucket. And so now you can notice that I have an XBI here and I have an XBI there. So I'm just going to put them together, and I'm going to invert this I minus gamma beta I. I can do that because there is a, right, this is an acyclic graph. So this matrix can be triangular if you choose the right ordering. And so now I have this times the X out of bucket parents plus this term, which multiplies our upper error term. And now I'm just going to rename the things here into, this will be called like lambda out of bucket parents bucket, complicated thing to say still, times X parents out of bucket parents plus these new var epsilon errors now, which hides kind of all this ugly stuff here. Right? Great. And so this is something that holds for each of these buckets. And so I've just written it out for one, and now we're going to put it all together to get like back our entire structural causal model. Right? So I'll just kind of put these blocks of these lambdas together in the right order to get back this system. So now X is equal to lambda transpose times X plus this var epsilon. So yes, Chris.
Can I ask a question about the calculation on the last slide?
Yeah.
I just want to make sure I'm following here. Where did I see an X on the right, on the right hand side, the top equation? I see an X BI and I see an X parents. How did that come together to be X parents?
Oh,
where did the XBI go, or is that something about
this one moved to this side that gave you this thing times XBI, and then I just inverted that and multiplied with this part. Right, so this part comes from here, and this gives you kind of this I. Does that make sense?
Is it a quality, or is that?
Oh, sorry. Oh, yeah.
Should there be a?
Yeah. I see what you're saying. Yes, I messed it up a little bit, so I could. Yeah.
Okay, that's clear. I just want to make sure.
Yeah.
Okay.
Yes. Yes, I could expand on this a little bit. The equality here.
That's totally.
Bit, yeah.
Yeah, well,
that's true.
Now I'm back.
Great. Thanks for. I will fix that in the final version of the slides. Great. Okay, so we can rewrite our structural causal model into this form. So what has changed now? So now we have that this lambda ij elements, they are 0 for everything. So if you have ij such that I is not an out of bucket parent of j. And another thing that has changed is that for these var epsilon errors, we still have that they're mean 0, but now, they're no longer kind of mutually independent within the bucket, but between the different bucket components, they are mutually independent. And so that's helpful. So this is really helpful. Okay, great. So under this reparametrization, we get a few nice things. So one, if you choose S to be kind of all the nodes that are ancestors of Y, not through A, then this total causal effect can actually be expressed just in this like kind of simplish form, I guess. Right, so it's these elements lambda AS times this times SY. Or if you prefer, you can say, I just want to estimate all the elements of my lambda and then do kind of path tracing rules on those. So I'll come to an example of that. So another nice thing that happens is if you have Gaussian errors, then these block components, these lambda parents bi just corresponds so the maximum likelihood estimator for these just corresponds to the least squares coefficients from these kind of multivariate regressions of this bi on its parents, out of bucket parents. And so this kind of process is what we call G-regression. So that's the estimator we propose. It's made up of that, right? So our idea is, okay, just estimate these individual lambdas through this type of G-regression estimator, and then you kind of can plug it into this to get your total effect estimate. And then we can make this claim that turns out to be true. For any consistent estimator, tau ay hat of tau ay, that is a differentiable function of the sample covariance, we know that our estimator that we propose, this G-regression one, will kind of have a smaller or equal asymptotic variance. Yes, great, perfect. I know it looks like I have a lot of slides, but it's just, I will get through it. Okay, great. So you might wonder, okay, what are these estimators? So that actually includes all of the covariate adjustment estimators, recursive regression estimators from Nandy et al. And kind of Gupta et al., as well as this modified Cholesky decomposition estimator proposed by Nandy et al. So they all fall under this, and our thing should be more efficient. So let's go to the example and just let me tell you kind of what kind of the plan is here. So now we're saying that in this case, this total effect, I can just replace here what would be that generalized G formula. We'll have this form. So you have xy given C and E, and then xc given A. So what this is proposing to you, if you don't want to think about estimating the entire lambda, is a plug-in estimator made up of two coefficients, right? So one is, so essentially get a coefficient from the regression of xc on A, and then you get a coefficient from y on xc and E, so get a coefficient next to xc, you multiply those two, that will give you your total effect, right? So you can decompose the total effect of A on Y as kind of the total effect of A on C and the effect of C on Y. And that ends up being the kind of efficient thing to do here. Okay, great. So let me just briefly go then through our simulation study. So we have simulated some results just to compare with these other estimators that we're claiming we're beating asymptotically. So we simulate data from a linear structural causal model with various error types. And then we choose our A and Y such that this effect is identifiable, because we're starting from that. And we'll compute the squared error because we're simulating so we can of kind of the true value minus what our estimate is and have that squared. And so we'll do that for all of the estimators. And so we'll compare our G-regression estimator to the adjustment estimator, this IDAM, which is this this estimator based on Cholesky decomposition from the paper of joint IDA, if you're familiar with that. And also compare with IDAR, which is also from the same paper, but it's based on what they call recursive regressions. And so we draw like a lot of these violin plots. And so what we're putting on these violin plots is just this, okay, so you all see, is this fraction. So it's the estimation error of whatever other estimator is divided by the G-regression estimation error. And so if it's bigger than 1, that means that the G-regression estimator is essentially doing better. So another thing to note here is that we're assuming in this case, I believe that we know the true DAG. So in this simulation, we're assuming we know the true DAG, but we're using kind of small, finite samples to kind of do all of these computations. So that's why you also see sometimes that values below 1 here, because our result is an asymptotic result, and obviously in practice that will not always be true. But you can see that if you compare with different estimators, so the first violin plot, so the one on the left in all of the plots, is the adjustments, the optimal adjustment estimator. The middle one is the modified Cholesky decomposition comparison, and the third one is the recursive regressions. And you can see that generally we do better than all of them generally, but we do better, much better than these second two compared to the optimal adjustment. So the optimal adjustment does actually pretty well. And of course, this is all if you know the DAG. One thing to mention is though that this is kind of comparison on these instances where we could estimate the total effect with all these methods, I believe. And I can be corrected if that's not true. But there are a lot of instances where these estimators kind of fail to identify the effects, so you cannot use them to estimate, where you can use the G-regression estimator. So this is kind of just a table showing that there are cases where, for example, you cannot use this estimator to estimate the effect, even though it's estimable. And same thing goes here, and you will see that the numbers here match the numbers here. That's because they both have the same kind of identifiability condition, even though it's a different estimate. Okay, and I'm out of time. So this is also given like an estimated CP-DAG. So you can see once you estimate, we don't do as well. I mean, the comparison is not as impressive, but it's still something. And if you're wondering, what do you do if you don't have a linear structural causal model, then you should come see Richard's talk on Wednesday here at the Berkeley Causal Inference Group, because we have some work on that. That's all. Thank you.
Now, thank you, Emma. And now we are taking a break and we will be back at 3:30.